Today's lesson, section 3.4b, we'll be talking about the upper and lower bounds theorem. So for the upper and lower bounds theorem, let P be a polynomial with real coefficients. And let's say if we divide P of x by x minus b, so a binomial, with b being greater than 0, using synthetic division, and if the row that contains the coefficient and remainder has no negative entries, then b is an upper bound for the real zeros of P of x. If we divide P of x by x minus a, with a being less than 0, using synthetic division, and if the row that contains the quotient and remainder has entries that are alternately non-positive and non-negative, then a is a lower bound for the real zeros of P of x. So what that fancy jargon means is that usually you have a set of values that can be x-intercepts, right? And so what they're trying to use to kind of giving you another tool, it's kind of like Descartes' rule signs in the rational zero theorem, is giving you another tool to help you narrow down where your zero should be in order to find all the x-intercepts. Okay, so here you're given the graph or the polynomial P of x is equal to 2x to the 5th plus 5x to the 4th minus 8x cubed minus 14x squared plus 6x plus 9. Okay, now I want to be able to find the upper and lower bounds of this polynomial. Okay, so I'm going to use the upper and lower bound theorem. So like it was saying, I want to use synthetic division. This is a very long one, so 5, 15, 6, and 9. Okay? And I want to be able to pick a value on the lower side. Now here you're going to have to check a couple numbers because it's a little harder to be able to find these zeros. Okay? So let's say we go with a higher number, so find the upper bound. So like they said, pick a b value that's greater than 0 and use synthetic division. So if I get like the line, the quotient and the remainder line, so it means this part right here, and it's filled with values that are not negative, so there's no negative entries, so all positive or 0, then that means that it must be an upper bound. Okay. Now you can always have a number that's smaller than that. Okay. So like here, how this would be useful is if I made my list for the rational zero theorem. So you do 9, 3, 1, and then 2, 1. Okay. So you'd have 9 halves, 9, and these are all plus or minus. Then you have 3 halves, and then 3, and then 1 half, and 1. Okay? So then, looking at that, you have values of 9 that are up there, and you want to be able to get rid of some of your values. So let's say Descartes' rule sign didn't help, so we want to use this to help us narrow the field to help us pick where we want to find some answers. Okay? So let's say we pick some number that is, let's say, I want to get rid of the big ones. So like 9 halves, and so 9 halves is like 4 and a half and 9. So let's say I picked 4. Okay. So if I put 4 in there, then do your same synthetic division. So that gets me 2, 8, 13. That'd be 52, and then that would give me 44, and then I would get 176, I get 162, I get 648, and 654, Now obviously these are very large numbers, but just to show the fact that they're all positive values here, that shows that 4 is an upper bound. So like looking over here, you could cross off the positive of 9 as a solution and then 9/2, so you wouldn't have to try those. You could even get smaller if you wanted to. Let's say we want to get rid of like 3. See if 3 is an upper bound or not. Okay, so let's go to let's plug in 2. So if I did the same thing, okay, then 2, then 4, 9, 18, 10, 20, 6, 12, and then 18, and then 36, and then 45. Okay, so they're all positive values. So then that means that 2 is an upper bound. Okay, so you can reduce this down as far as you want. 2 is actually the smallest one, because if we went to 1, then it would not give us the same thing. So let's say the upper bound is 2. Okay, and then now let's try a lower bound. So let's say let's try with the -4 that we did before. So the opposite sign. So get rid of like a -9/2 and -9. Now for -4, when you're doing the negative ones, so if you're looking for a lower bound, you want them to be alternating, non-positive, non-negative. So that means that you could be 0 could be in there. Okay, so the first one is probably going to be positive because you have a positive coefficient to begin with, so 2. So then the next one needs to be 0 or negative for it to work. Okay, so then multiply -8, I get -3. Okay, so it's negative. So the next one needs to be positive. So I get 12, gets me 4. Okay, it is. Then the next one needs to be negative. So I get -30. It is. The next one needs to be positive. And it is. And then the next one needs to be negative. And it is. So it had the alternating pattern of going from non-negative to non-positive every time. And so then that means that -4 is a lower bound. Now the next thing is to think, is it the smallest? And so if we plugged in -3 would give us something. You can test that out if you'd like. But -4 is the lower bound of this polynomial. So there's your upper bound is 2 and your lower bound is -4. Okay? Let's try another one. So here I have x cubed minus 3x squared plus 4. This one will be a little easier to check out. So let's look at that list that you have. So then you'd have 4, 2, 1 over 1. So then your list would be plus or minus 4, plus or minus 2, plus or minus 1. Okay? So here let's say that we want to get rid of the 4s. So if we did, let's say, 3, okay, so you add down 1. So remember, for the upper bounds you want all the same positive non-negatives. Okay, so then 3, that gets me 0, 0, 4. Okay, so they're all non-negative, so the 0 is okay. So then that means this is a candidate for an upper bound. Okay, now let me show you, since I have more room here, let's try doing 2 and see if that is an upper bound, even though it's a possibility for a 0. Okay, so if I do 1, 2, -1, -2, and 2. So here, because that one was negative right there, that means it's not an upper bound. So 3 is the highest you can go. So upper bound's 3. Okay, then let's try our lower bounds. So let's do the same thing. -3. So then 1, -3, 4. So 1, -3, -6, and then 18, 22. Okay, so that one is a candidate for a lower bound because you have alternating values, a positive, negative, or non-negative, non-positive. Okay, let's try a smaller one. So -2. So 1 gets me -2, -5, and then multiply gets me 10, gets me 14. Okay, so that one's a better one. So this one's not the lowest, this one is so far. Let's try another one. So let's go to -1. So 1, B, -1, -4, and then 4, that'd be 8. Okay, so then that one is a lower bound. So then this one's a lower bound. So this one's not the lowest anymore, this is the lowest. Okay? Now, obviously there's nothing lower than -1, so we just stick with -1. Okay? And so then that's our upper and our lower bounds. Okay? Now, this is just a tool, remember. Just like Descartes' rule of signs, sometimes it's helpful, sometimes it's not. It might be helpful with polynomials that have less terms in them, like this one. Unlike the first one where there's lots of terms, so it takes a while to do all the computations for synthetic division. So it might not be effective or efficient to your time to be able to do this all the time for your stuff, unless you have a lot of numbers. So like if your list for rational zeros is very long, then maybe this is very effective or a good use of your time to cut out a lot of those bigger values, so you know that none of these are options, so I can just narrow my search a little bit better. But sometimes when it's like with 6 possibilities here too, you could try these easily and spend the same amount of time just finding those zeros rather than figuring out which ones are not and then going from there. So it'd be about a wash in that sense. So remember, it's a tool. There will be problems that ask you to just find the upper and lower bounds, but for if you're doing finding the real zeros of your polynomials, know that you don't have to use it unless you feel like it's going to be helpful to you. Okay? Have fun.